Okay, it started. You can introduce the speaker. Krishna.
Oh, okay, sure. So we can start.
Yes.
So it's a great pleasure to introduce Kamalakshya Mahatab. He's an Inspire Faculty Fellow at CMI currently. He's just probably completed a long postdoc at the University of Helsinki and many more postdocs before that. Sorry, I'm not fully able to remember. But before that, we have had a long association when we were both PhD students at IMSC. So I recall those times very fondly. So it's over to you, Kamalakshya. Please go ahead.
Thank you, Krishnan, and I'm very happy to talk to you after a long time, and also very happy to give this talk. So, and thank you for the invitation to both also Gaurav and Arthur. And yeah, so yeah, let's begin. So I think most of us are number theorists, but I still prepared some basic slides, so please don't mind on that. Okay, so we'll start. Is my voice okay? Okay.
Yeah, it's fine actually. Go ahead. It's perfect.
Yeah. So. Yeah, so let's start. So today we'll talk about argument of the Riemann-Zeta function. So it's in fact a very important aspect of Riemann-Zeta function. Like, so generally this argument function, it has a nice Dirichlet series expansion, and that is used like to understand different properties of the Riemann-Zeta function. So we'll talk about today what is the size of this argument and how it behaves. So let's start. Let's start by recalling Riemann-Zeta function. Okay, so here all of I think most of you are number theorists. Still, I think we'll have some basic slides. So let's recall that this Riemann-Zeta function, it is given by an absolutely convergent series. And then there is an analytic function except for a simple pole at s equal to 1, analytic function on C, which matches with this Riemann-Zeta function. So it has an analytic continuation to all of C. And further, it has a functional equation. We write zeta is equal to chi s times zeta 1 minus s, where this chi is a ratio of the gamma function. And what is the, in theory of Riemann-Zeta function, understanding the zeros of the Riemann-Zeta function is very, very important. So let's talk about the zeros. So there are two kinds of zeros of the zeta function. One are called trivial zeros. The trivial zeros, they comes from the poles of this gamma function we saw in the functional equation. And then there are non-trivial zeros. And how this non-trivial zeros comes, that's very mysterious. And in fact, that's kind of open problem till date. So, so there is a conjecture which kind of try to describe like how these zeros are. So this is called the Riemann hypothesis, which is very famous, and we are aware of it. So it says that if we have a non-trivial zero, that means if it has a real part between 0 and 1, then its real part has to be half. Right, and today, throughout this talk, we'll assume Riemann hypothesis to present all the results. Okay, so and what is progress towards this Riemann hypothesis? It's very, very little, and the best known result, which is way back due to Vinogradov and Korobov, which says that this zeta is not equal to 0 in a very narrow strip close to the 1 line, which is like 1 minus 1 by this log t power and double log t power. Here I use this notation log 2t, which would mean log t. And I will keep on using this notation time to time in this talk. So I'll use the notation log kt to denote log t iterated log iterated k times. Okay, and here is a basic picture of how the zeros are distributed. This gray region is Vinogradov-Korolov's region, like which is proven to be zero free, and on the rest of the white region in this strip, we don't know where the zeros are, and Riemann hypothesis tells that all the zeros are on this half line. Okay, so let's recall some basic notations. So we say fx is less gx if fx is less equal to some constant times gx after some x greater than x naught, and for a positive constant c. So here here the signs of f and g will matter. Okay, so and if we have fx equal, we'll write fx equal big of gx if mod of fx is less gx. And we say fx equal to little of gx if fx by gx extends to infinity, that goes to 0. Okay, so let's come to what is argument of the Riemann zeta function. So the argument of the Riemann zeta function, so let's say it's arg of zeta s. So argument is supposed to be a multi-valued function. So we have to choose a branch, right? We have to choose some values. So how do we make choice? So let's recall that this zeta on the real positive line, the value of zeta are also real and positive, right? So if we have zeta of 2 or 3, these are all positive real numbers. Let's say this, let's just define that argument of zeta 2 equal to 0. And then we try to define argument of zeta s by in the critical strip by shifting then we define we travel along the path from zeta 2 to zeta 2 plus it, and then zeta 2 plus it to zeta say to s equal to say half plus it. Suppose you want to define argument on the line half plus it. So and with and along this path we'll vary the argument continuously. Right, we define it to be a continuous function along this path. Starting with 2, going to 2 plus it, then to half plus it, and at half plus it, will whatever value we reach, that is to be the value of the argument of zeta half plus it. So we can do this process provided that we don't encounter a 0 on this path, right? So we should not. So there should be no non-trivial 0 of zeta that has ordinate t. Then this argument of zeta s is defined. In fact, we can define argument of zeta sigma plus it in the same way. Not only on the half line, we can define at any point on the critical strip. And once we define argument of zeta, we'll say s of t, which is equal to, which is this normalization of this argument, 1 by pi argument of zeta half plus it. Okay, and if we encounter a 0 on our path, then what we do? Then we define the argument by taking average of the values in the neighborhood. We define s plus t plus epsilon and s t minus epsilon, and we average it, and epsilon goes to 0. That's supposed to be our s of t. Okay. Now, since we defined the argument, let's see. Okay, let's see some result involving argument. This is a very famous result called Riemann-von Mangoldt formula, which counts number of zeros in the critical strip up to a height t. So n of t denotes zeros that are in the critical strip. These are non-trivial zeros, and its imaginary part is between 0 to t. So its height is maximum t, and we count all these zeros. We say n of t. Then n of t has such a formula. So we see that it's a formula involving elementary function and s of t and an error big of 1 by t. Note that this n of t, this is a counting function. So for large t, this big O of 1 by t doesn't matter really, because it's a very small number, because n of t is always always a positive integer. So this has to, this suppose this should not matter at all. So here we see that if we really understand S of t, then we have a actual formula for n of t. Right. So that's why S of t is a very important function, because using that, this is one example that why S of t is important. So using this, we can actually estimate how many zeros are there up to height t. Well, or we can find a very explicit formula. If we have a formula for S of t, we can find an explicit formula for the number of zeros. This is one example, and there are many cases where we use S of t to calculate several information about the zeta function, including its distribution too. So let's see some results on S of t. How large is S of t? So this is a result of Carnero, Chandy, and Milnovich, which is under Riemann hypothesis, which says that S of t is less or equal to 1 by 4 times log t by double log of t with some error. And this is the best possible result. And we also know that improving this is very, very difficult problem. And if you ask, like, what is without Riemann hypothesis? Without Riemann hypothesis, the best we can say is that S of t equal to big O of log t. That's the best we can say. Okay, and now we may ask what are the, okay, this is the upper bound, but what is the true bound of S of t? So we may ask what are its lower bounds. These are some results in this direction. First result is due to Montgomery, who says that positive and negative values of S of t are at least of order log t by double log of t. Okay. And there is a result which uses this resonance method, and which says that absolute value of S of t is at least this large. And this is an improvement of the Montgomery's result by this triple log of t factor. Okay, square root of triple log of t factor. So though Bondarenko and Seip's result improves Montgomery's result, but it doesn't say which value of S of t are large, whether the positive value of S of t are large or whether the negative values of S of t are large. Some we know just that one of these is large. Okay, so today's talk we'll try to understand this problem. So which value of S of t, mod of S of t is large, and this is the best result we can prove using resonance method. Like if we try to improve, we can only improve this constant C beta if we try to want to calculate this explicitly. Otherwise, this is best we can do. Okay, so so what is the true value of S of t? What should be the conjecture? So the conjecture that uses some this random matrix theory, and it's due to Farmagonek and who says that S of t is the order square root of log t and square root of double log of t. Note that the known lower bounds are even quite smaller than the conjecture. So we even don't get square root of log t. It says that it's larger than even square root of log t. Still, there is a large kind of distance to cover here and in terms of the estimate of S of t. Okay, so what we can prove about large positive and negative values of S of t? This is a result with Chire. So we assume Riemann hypothesis. In fact, today all the results we assume Riemann hypothesis, and it so that this plus minus of S of t, positive and negative values of S of t, have this magnitude, which is same as the result of Bondarenko and Seip over here. Right, so they have this result without saying the positive and negative values. They don't account for the signs, and in this result we do that. We know that the positive and negative result, negative values of S of t have this magnitude, and this improves Montgomery's result and as well as Bondarenko and Seip's result. Okay. So let's see how the proof works. We'll have a very brief sketch of the proof. So it has two parts. First, we want to construct a convolution formula. Why we want a convolution formula? Because we want to use this resonance method. So somehow the actual formula for, the formula of S of t in terms of Dirichlet series, that is difficult to work with. So we need a modification of that, which will be our convolution formula, and it will have a completely positive and completely negative kernel to account for the sign changes. And then we want to construct a resonator that will use to find large values of this convolution formula. Okay, so let's talk about the convolution formula. Okay, so here it looks a bit kind of with too many terms, but let's try to understand this. So this is a convolution formula for log zeta on the half line, half plus it. Right. And what we see here, we have a this is a positive kernel. So sine lambda u double log t by u square. So this is always positive. And then we have this plus minus 3 minus 2 sine u double log of t. So if we choose plus 3, then this makes this whole kernel positive. And if we choose minus 3, then this is always a negative number. And this makes this whole, this is a, yeah. So this makes this whole, kernel is negative. Right. And on the right hand side, what we have, on the right hand side, we have a Dirichlet series. And note that this Dirichlet series, this Wn equal to max 0 and this 2 lambda double log t minus these values in the absolute sign log double log t minus log n absolute value. So this Wn has a it has a compact support. It's the famous triangle function, right? Which comes by, from the Fourier transformation of this sine u by u square. Okay, and all the coefficients of this Dirichlet series, they are positive, right? And we have a I in front of it, so we have a imaginary, completely imaginary number in front. Okay, and we have some error over here. Let's try to see how we can derive this convolution formula, which is not very difficult. For that, we need to derive first this convolution formula, which comes by using Perron's formula. So, okay, let's take this to be granted that if we expand this log zeta, we'll have some expansion. So we can use the analytic properties of log zeta and use this kernel sine alpha u by u square e power I h u du, and then you'll get this series over here. Okay, so here we notice that we again have a Dirichlet series with completely positive coefficients, and this series also has finitely many terms because we have Wn is a finitely supported function, right? And what else? Okay, unlike before, we have the terms in the previous series, they are imaginary, right? And here we have all, we have a mixed term. We have this as real part as well as imaginary part. This Dirichlet series has both coefficients. So you may ask what happens to the real part that kind of absorbed in this error log t power lambda. Okay. So let's assume this theorem, and we have these two parameters alpha and h can be any real number. Alpha is bigger than 0. Now what we do, we will choose a value of alpha which will be fixed, and then we'll choose different value of h and make a linear combination to derive this formula. How do we do that? Okay, so we choose alpha to be lambda double log of t, and h equal to either we'll choose 0 log t and minus log t. And we'll make this linear combination. So we'll make plus minus 3 with the first choice and multiply this equation with plus minus 3. And then we multiply I e power I double log t u with the choice log 2t or log t, and minus I with the choice minus double log of t. And we make this linear combination, and since this e power IHU, that is kind of separated in this kernel, so this will I mean, in the exponent it will behave like linearly, right? So and if we do that, we'll have like plus minus 3 minus 2 sine double log t u in the kernel. Okay, so yeah, so now we plug in these values, and in this equation 3 different values, and we add these 3, we get this value. And okay, so that comes on this kernel. What happens in the right hand side? So what happens if we have this last choice minus double log of t? So if we have minus double log of t, here we have lambda double log of t to lambda double log t, and lambda is between half. So lambda we have between 0 and half. So this is 2. So we have 2 lambda double log of t, and if we have minus log t over here, yeah. So if you have minus double log of t over here, then log n and minus log t, that is larger than 2 lambda log t, because 2 lambda log t is always less than lambda log t, because 2 lambda is less than 1, and this will be dominant, but since we're taking max of 0 and this term, so this will be always 0. So this series on the right hand side, this will just cancel out. This will be completely 0 for the last choice of S, and the other 2 choices of H will survive. Right? So we have we will get this series, right? So this plus minus 3 on the right hand side will give this Dirichlet series, and this multiplication of I will appear on the second part of this Dirichlet series, right? I pi by 2. Now we get our convolution formula if we can show that this the first part of this Dirichlet series, this is very small, right? This is absorbed in this error term, which is log t power lambda, and that happens because of our choice. There are very few terms on this on the right hand side sum. Sorry, on this left hand side sum, right? So we can show that this sum is non-zero if we have for n up to log t power 2 lambda. Okay, so recall this the definition of wn lambda double log t 0, and so if we have so it's alpha is lambda double log t, and h equal to 0, we have log n, and so log n will be maximum of 2 lambda double log of t, right? So that means n is of the can be up to log t power lambda, log t power 2 lambda, right? So we have log t power 2 lambda terms, and so we can make this sum instead of 2 to infinity, it goes up to log t power 2 lambda, and this lambda n, which is the von Mangoldt function, this is equal to log n if say if n is a prime number, and it's so if n equal to p power r, lambda n is log p, right? So for the primes, this lambda n and log n, that gives just 1, and we have 1 by square root of p, which we sum log t power 2 lambda, and for other p powers, this sum will have very small contribution, and so this is the dominant part, and if we sum 1 by log t power 2 I mean 1 by square root of p we'll get this log t power lambda over here. Okay, so that's using this prime number theorem, we can get this value. Okay, so now we have, and given this, we have our convolution formula over here, and we'll use resonance method on this convolution formula. Let's see how we'll use the resonance method. Okay, so what is this resonance method? This resonance method kind of it uses a kernel, and it's then we want to find the integration of a function with the kernel, and then you divide that by integration of the kernel and say that we'll get the large value. So first of all, it uses a resonator R of t. So how should R of t look like? So R of t should mimic the behavior of the original function. In our case, since we are working with a L function, it has a Dirichlet series. So our R of t should have a Dirichlet series. If you are not working with the L function, then we can change the resonator to be anything that kind of looks like that function. So we have R of t, which is sum of Rn by n power sigma plus it, and this and Rn can be anything. Like for today we'll have this to be real numbers, but it can be anything. It can even be complex numbers, right? So and then we use the resonator in this way. So let's observe. Let's see what is happening over here. Suppose we want to calculate this, right? Plus minus positive and negative values of S of t, positive and negative large values of S of t in some interval. Then let's consider this integral on the right hand side. We have S of t plus u, and this sine u by u function square, and we have this kernel plus minus 3 minus 2, and we have du rt square phi t by t dt, and this phi is the Gaussian function, which is e power minus t square. Okay, so how do we estimate this? Let's observe. So we can take this S of t plus u out like this. So we can just take that this is larger than this thing. Right? So we have maximum plus minus of S of t in this interval. Why? So we have t varies in this interval, t per beta to t log t, and then again u varies minus log t cube to log t cube. So t plus u would vary t power beta minus log t cube to t log t plus log t cube, right? Which is inside this interval, right? So the maximum will be so this maximum will be larger than the maximum in this. So this value is larger than this s t plus u. So this goes out. Now what remains? Now this integral minus log t cube to log t cube sine u by u square. So this sine u by u square, that is a bounded integral, but we have a double log t over here. So we normalize this double log t, and after normalizing, we'll get a double log t from this interval, right? From this integral, right? So if we exclude s of t here, and if we calculate this integral, then we'll get double log of t. And now whatever remains is the integration of rt square phi t by t dt, which is on the right hand side, right? So this formula is clear, right? I hope, you agree to me that this is correct, right? So now we'll use this to find this max of plus minus of S of t. So what we need to find? So we need to find some a lower bound for the right hand side, and we need to find a upper bound of this integration of rt square phi t dt, and then we'll have then we'll divide both of this, and we'll get this maximum of plus minus st. Okay, and how do we find the lower bound of this S of t plus u? So for that, we'll use our convolution formula. So we know that this convolution formula over here that has a Dirichlet series expansion. So let's see that. Okay, now for now we'll use our resonator on our convolution formula. So let's understand what should be the resonator. So the resonator will use the resonator that was used by Bondarenko and Seip. They have constructed this RM quite explicitly. We'll not get into the very detail of this resonator. We'll just say, state some properties and see what are things that are important for us to give large values. Okay, so this resonator of Bondarenko and Seip, so they used it to find large values of zeta half plus IT. And before them, there were other attempts. So the best known attempt was due to Sundararajan, who used a resonator. In fact, from his paper, he kind of popularized this method, and other mathematicians started using it. So, so he used a resonator, and it has a very, which uses a very limited number of keys. And the difference of Bondarenko and Seip's resonator to that of Sundararajan's resonator is that it was able to use a little bit of more number of primes. Okay, so even the large values of zeta half plus IT that was known before, which was due to Montgomery, that also uses a very limited number of t, but that doesn't use resonance method. Rather something called a Diophantine approximation method. So it uses Dirichlet's theorem to find large values. So the previous authors, what they do, they use this number of primes up to log t and double log of t, and then you'll not get a triple log of t factor. So what was like breakthrough in this paper of Bondarenko and Seip is that they have extended the range of p to have like more number of primes. Right? We have like number of primes log t power, let's say 1 plus epsilon number of primes. Right? This is bigger than that. So they have done that. Okay. What happens in this method is that okay, so they construct some multiplicative function fp, which has this this complicated formula over here, which comes from many previous work and some tries here and there. You try to construct this f of p, and this f of p takes value in some set of primes, some subset of primes in this range. Okay, and then our resonator, like coefficient Rm, is that comes from f of n by considering this. This is kind of, okay, we take kind of a norm of this f of n. So f of n square, we take it in a certain range and take the square root. Okay, so it's kind of an average out of this n. Okay. Now, what we use in our method? So we are able to get large values of s of t with our convolution formula, because the number of terms in our convolution formula, it is of order kind of log t power 1 plus epsilon. Why is it so? Let's have a look again at the convolution formula. Okay, it's here. So how many terms there on this right hand side? So we have this term lambda double log of 2 lambda double log of t, log low t, and log n. Now, so this will have terms log t power 1 plus 2 lambda. N can be up to that range, right? So it can be of order log t power 1 plus 2 lambda, and we'll have a lower bound log t power 1 minus 2 lambda. So the range of n we can get is of order log t power 1 plus 2 lambda. So the important thing is a little bit bigger than log t. Yeah, so a little bit bigger than log t power 1 plus epsilon. And that's what makes it like work with the resonator of Bondarenko and Seip, and where they need primes little bit little bit more than log t power 1 plus epsilon, or around log t power 1 plus epsilon. Right? So that helps. And we use this resonator, and we can prove such a theorem. So this is due to Bondarenko and Seip again. So we take this Dirichlet series, which appears in our convolution formula, lambda n wn by log n power half plus it, where wn has the same definition what we have in the formula before. And if we take this, then and integrate with the resonator, we'll get this expression. So this the terms under the square root that will contribute kind of to the large value of this Dirichlet series, and this t will kind of cancel with the t times the sum of FL square. That will be that will cancel out with this with the integration of the resonator, and this w mean wp that will kind of accounts for this wn. So and this will be of this will be maximum of order double log of t. Right. So let's have that, and then we apply all these things we have constructed till now to get the large value. So we saw that we need a upper bound for this RT square PT by TDT, right? So in the beginning, in the beginning over here, so to calculate max of plus minus S of t, we need a upper bound for this and a lower bound of the right hand side. And lower bound instead of the right hand side, we know from the convolution formula, this is equal to a Dirichlet series. So we'll calculate the lower bound on the right hand side. Okay, so where we are, so we have such a upper bound. Now we want to calculate the other side. So why we can use the convolution formula? Note that how if we in our okay, so this term on the right hand side, this we can get by taking the imaginary part of our convolution formula. Just a minute, excuse me, I'll just put just 1 minute. Sorry for the break. So I get my internet from my phone and it was going to be switched off. So sorry for the disturb. So let's get back where we were. Okay, so on the right hand side, the term we have that comes by taking the imaginary part of a convolution formula. Let's see why. Let's get back to the convolution formula. So we have, okay, what happens if you take the imaginary part? So we'll get some some pi times S of t, right? So some constant times S of t plus u, and everything remains as it is because all these terms are real. And then on the right hand side, we'll have since we're taking imaginary part, we'll just like take out this I and we'll have this term, right? Like why? Because once we put this resonator over here, like RT square Pt by T dt, then each term will be positive. Okay, so so if we take the integration of n power half plus it, RT square yeah. So if we take the so if we integrate with this RT square Pt by T dt, n power it. So it will always be positive because RT has for our resonator RT the coefficients of RT are positive, and this gives a Dirichlet series expansion, and then we are using the Gaussian kernel. So if we take some n power anything, and if you take a Fourier integration of this Fourier transformation of the Gaussian kernel, then it always gives a positive term, right? So that's why we'll always have positive terms when we integrate this right hand side with RT square phi t by t dt. And when we take the imaginary part, we'll just keep this I, and we'll have this series integrated with RT square phi t by t dt. Okay. So, so we know that now. So this is the imaginary part of our Dirichlet series. So we have a formula here, and we saw again that this formula have this large value. So it's less or equal to t square root of log t triple log t by double log t, and this mean term, and then sum of FL square. So that this gives the lower bound of our right hand side term. So using that we get t log t and sum of FL square, and double log t we already had, and on the right hand side what we had before, we have this term. And now once we cancel all these extra terms out, we'll get our theorem, which is plus max plus minus of st. It's greater or equal to log t triple log t by double log t, and that gives the result. Okay, I hope it's clear. And this is I wanted to say about the proof. Okay, and if anything not clear, we'll talk about it after the talk. So now there are few generalization of this argument of zeta on which we can use the same method and try to get the large value. So there are some more applications we discussed in another paper with Chire, which I'll just talk about those results very briefly. So like S of t, we can define S sigma t by half of argument of zeta sigma t. And again, we can define argument of zeta sigma t like we define argument of zeta half plus it by continuously varying the argument along a polygonal path, right, which doesn't encounter a zero. And again, if we encounter a zero, then we take this limit epsilon goes to 0 half S sigma t plus epsilon and sigma t minus epsilon. Average of that, and we know that S of t is S half plus S half t, which we discussed before, and then we can define Sn by taking the iterated integrals of S. So we define this inductively. So let's define S naught of sigma t is S sigma t, and Sn of sigma t is integration of Sn minus 1 sigma tau d tau with some kind of extra term which depends on n and sigma, say delta n sigma. Okay, and this has an expression like with several integrals. So and we write Sn t to be Sn half t. Okay. So these are all the notations, and with all this, so let's see some more results. So this is okay. This is with, about S of t again. We didn't use any new notations here. So this is a result we proved with Chire under Riemann hypothesis. So it proves large value of St plus h minus S of t. So this difference of S of t in a very small interval with sign minus, and we prove that it's legally so it has this low bound. And but we could prove this result in a very narrow interval like this. Okay, and this improves the Selbach's result. However, Selbach's result is true in a much larger interval. Right. So yeah. So it improves the Selbach's result by a lot, but in a very narrow interval. Okay. So what are other results? So there are some results known about Sn of t under Rh. This is due to Selbach. This says that Sn plus I mean positive and negative values of Snt is this less. Note that though Snt is defined like in terms of iterated integral, intuitively it's supposed to be larger than S of t, right, on each stage of the integration, but we kind of prove a smaller, I mean, somehow it happens to be the smaller value. Once we integrate, we make the variations of the S will be more and more stable with each integration. So Selbach proved that this is log t power half, double log t power n plus 1, when n is congruous to 0 and 2 mod 4, and with a little bit better factor when n congruous to 1 or 3 mod 4, which is of order triple log of t square root. And here are some results of Chire, who improves Selbach's result by adding this extra triple log of t power square root, which kind of improves the result in case of this n congruous to 0 or 2 mod 4. However, Selbach's result considers, I mean, it accounts the signs of Sn of t, but this Chire's result, it doesn't account the signs, and the reason is that it uses the resonance method, and initially we didn't know about this kernel, so these are the best known results one could prove that time. Then later, once we have discovered this kernel, we could use this completely positive and completely negative kernel to account the signs of Sn of sigma t or Sn of t. We can roughly say it's Sn of t. It's a very narrow, in a narrow neighborhood of the half line. So this improves Chire's result when n is even. So if n is even, it doesn't say anything about a sign, it just uses absolute value. So here we prove plus minus of 1, and for n is odd, we I mean, for n congruous to 1 mod 4, we don't improve in this result anything, but for n congruous to 3 mod 4, we get a negative sign over here, right? So we could prove large negative values. So it proves large negative values large positive values for n congruous to 1 mod 4, and here we prove that along with large negative values when n congruous to 3 mod 4. Okay, so so these are all the results I wanted to say today. Okay, there are few things one can work. Like there are few research problems one can work on. Is that okay? So here, for example, we prove large positive value for Sn of t when n is congruous to 1 mod 4, and large negative value for Sn of t when n is congruous to 3 mod 4. So maybe one can try to prove the large negative value for n congruous to 1 mod 4, the same as it is for large positive value, right? That is one open problem. So let's say even for S1, to find large, for S1, find large values of order log t, and we have triple log t power half, and we have n power 3 by 2. So prove that minus of Snt is this large, minus of S1 of t is this large value. So this is one open problem. And same for n congruous to 3 mod 4. And also another problem is to trying to apply this method for zeta sigma plus it when sigma between log of zeta sigma plus it when sigma between half and 1. So we want to find large negative values of log zeta sigma plus it. And so this is also another nice problem to try. So these are all the results I wanted to say today, and this comes from these two papers, and thank you for your attention.
Thanks a lot for that nice talk, Kamalakshya. Do we have any questions or comments from the audience?
Yeah, I have a question.
Yeah.
So in your lemma, how this Riemann hypothesis come into the pictures?
In the convolution formula.
Yeah. Yes.
Okay. So in the convolution formula, we kind of use this Perron's formula, right? So we need to shift the line of integration to have these terms, like, so that uses this Riemann hypothesis.
I see. And then so if you define this S and T, so do you have any application? I mean, like how this size is, where this size is applicable?
So if you try to calculate, what is SNFT? So SNFT kind of make the normalize this variation of S of T. So in SNFT, the oscillations of S of T kind of it becomes small and small. And other thing is that if we want to calculate, say, this problem, so try to find sum of gamma n power k, where gamma n is up to an ordinate of t. Where gamma n are the ordinates of the zeros of zeta. And how do you do this problem? So you'll get a similar formula like Riemann-von Mangoldt, and this Sn of t will appear there. And there are several other applications. So this is one sense.
Okay. Okay. Thank you.
Can I ask a naive question? I've forgotten many things. So this is already known that Riemann hypothesis has infinitely many zeros on half line, right? Or what?
Yeah, Riemann hypothesis conjecture that there are infinitely
No.
Okay, this is this is known that one can prove there are infinitely many.
1 minute, there is a plane going. I can't hear. So sorry.
Oh, sorry.
So tell me again.
So, I mean, without assuming Riemann hypothesis, we can prove that there are infinitely many zeros on the half line.
Okay.
But Riemann hypothesis says that all the zeros.
Okay. So that's, I wanted to know that.
So that kind of.
Okay. Yeah. But positive half line, right? Means, can you show that the negative half line has no zeros?
Negative half. Okay, no, the zeros are symmetric along the x-axis.
Oh, okay. I see. Okay.
So if you have a zero wherever on the positive plane, you'll have exactly the same replica on the negative plane.
Okay. I see. Okay, so since there are, but I mean, okay, infinitely many zeros, but that they go, their value, imaginary value goes to infinity, that's also known, right?
Yes. Yeah. So that in fact proves the zeros are infinite. In fact, you can show that the zeros are kind of quite discrete, so you can always find a neighborhood.
Okay. So they don't have a.
So
they don't have a limit point. Okay. On half line.
Yeah, they don't have a limit point.
Okay, that's good too. Thanks. I've just forgotten. I read the book long ago, but yeah.
I had one question, Kamalakshya.
Yeah.
Hi. So this iterates of S that you took, this Sn, how to, I mean, what kind of information is it giving if you want to understand? Is it like average of the argument or?
Some sense, yeah. Some sense, it's kind of iterated average, like we have an average and we take another average and so on. So it's so S of t is kind of very random, like it has like large amplitudes, and S1t will have slightly smaller, S2t will have slightly smaller, and so on.
Because you're integrating again each one.
Yeah.
Okay.
It makes it a nicer function, and of course, I mean, how we apply it, that depends on like the mathematics and how you want to use it for different problems.
Okay. And this positive values of S and the negative values, we are expecting it to be sort of, I mean, though we are expecting them to be symmetric and have the same bounds, the same, attain the same large values, say.
I think that can be a conjecture to show that it's always be same. So yeah,
Okay.
so it's still, I mean, it's a open problem too, so that it's not skewed towards positive side or to the negative side.
Right. Okay. So far, nothing to show that it is skewed.
Yeah, so we don't know anything about it, so
Huh.
that's
Okay.
a problem to work on.
Okay. All right. Thanks.
Just to continue on that, what was the expected size of Sn of t? I mean, are there random any conjectures?
No, that's also a very open problem, and in fact, that's kind of a doable problem, that using random matrix to find a similar result that I mentioned of homogonic can do.
So
Yeah,
there will
that's
be
kind of a problem.
a log in n. Sorry, log
Yeah,
2
we're
to the
supposed
n
to expect a double log of n factor.
in the denominator.
Sorry, double log of t power n factor in the denominator, but we don't know if that is true or what. I mean, what will come out. We don't know. So
Yeah, as you
I
said,
think
it sounds doable.
yeah, that's a doable and that's a very nice problem to work on. Yeah.
But nobody has made any conjectures like Selberg, for example.
No, the latest is using this random matrix by this, Farmago and yeah, so using those along those lines, one can try to find this evidence. Yeah, it's yeah, one's supposed to do that.
Okay, if there are no more questions, good. Thank